Welcome to the third video in our series on linear programming. This video will take us through the Simplex method. The Simplex method can be quite challenging, so take your time to work through the calculations. Let us consider our learning objectives for this video. First, we need to learn how to formulate the problem algebraically. This will be done by identifying and developing the input constraints. Once this is done, we will develop the objective function. Remember, we are trying to either maximize or minimize the objective function, depending on our goals. You should remember how to achieve these objectives from our video on the graphical method, so we will not spend too much time here. After we have done all the preliminary work, we are then ready to solve the problem using the Simplex method. To do this, we will learn to set up the initial matrix and then derive and interpret the final matrix. Finally, we will calculate the shadow price of a resource using the final matrix. To work through the Simplex method, we will use the same example that we used under the graphical method. Let us break the Simplex approach into some steps. As with the graphical method, the first thing we want to do is to identify the constraints and determine the objective function. Notice this time that we are not plotting these on a set of axes. The axes limit us to two products only. Rather, this time we are going to use the constraints and objective function to set up the initial matrix. The use of a matrix gives the Simplex method the ability to determine the optimal solution when more than two products are produced. After we have set up the initial matrix, we need to calculate the final matrix and then interpret the final matrix. Based on what you learned under the graphical approach, take a moment now to pause this video and see if you can develop the constraints and objective function on your own. Great, so our constraints are now on screen. If you can't remember how we arrived at these constraints, please revisit our second video in the series on the graphical approach. Now, in developing our initial matrix, we need to remove the inequalities, which are the less than or equal to signs, and replace them with equals signs. To do this, we need to introduce something called a slack variable. The slack variable represents any potentially unused capacity of the constraint. So if we look at materials, in order to fully utilize the 3,440 materials, we would have 8 multiplied by the production of A, plus 4 multiplied by the production of B, plus S1, representing any potential leftover materials. Notice again that we have changed the less than or equal to sign to an equals sign. Now we do this for all the remaining constraints. So labor is now 12A plus 16B plus S2 equals 5,760 labor hours. Machine hours is now 8A plus 10B plus S3 equals 5,520 machine hours. Product A sales is now 1 multiplied by the production of A plus S4, which represents any remaining demand, and that all equals 450. Notice that we leave off the constraints of A and B must be greater than 0. Our objective function then remains unchanged. Now the final step is to make the slack variable the subject of each constraint. To do this, we simply swap the formula around until the slack variable is on its own. So for the materials constraint, we get S1 is equal to 3,440 minus 8A minus 4B. For labor, we get S2 is equal to 5,760 minus 12A minus 16B. For machine hours, we get S3 is equal to 5,520 minus 8A minus 10B. And finally, for product A sales, we get S4 is equal to 450 minus 1A. Again, our contribution formula does not change. We are now ready to set up our initial matrix. In our initial matrix, we have 4 columns. The first column represents the unused quantity of resources should we produce absolutely nothing. The next 2 columns represent our product's usage of the various resources. We would add more columns for each additional product we produce. So if I had products A, B, and C, we would have an additional column for product C. The last column is then just a description column, so we can keep track of what we are looking at in each row. You can see that I have already labeled the rows based on the constraint that we will put into them. Now we need to put each constraint into the matrix. For the materials constraint, if we produce 0 units of both product A and B, we will be left with 3,440 units of unused materials. Our unused materials, represented by the slack variable S1, is 3,440. We then ask how much product A uses of materials, and we see that for each unit of product A, we use 8 materials. So we can enter this into our matrix as -8. The same then applies for product B, which we can enter as -4. We can now apply the same logic to labor, and we get S2 is equal to 5,760 in the quantity column. We get -12 in column A and -16 in column B. Now pause the video and try the next 2 constraints on your own. Great, you've got this. For machine hours, S3 is equal to 5,520 is in the quantity column. We have -8 in column A and -10 in column B. For product A sales, we have S4 is equal to 450 in the quantity column, -1 in column A, and 0 in column B. Our last step then is to deal with the contribution line. If we produce absolutely nothing, our contribution will be 0. So in our quantity column, we have C is equal to 0. For each unit of A we produce, we gain a contribution of 20 Rand. So column A's value is positive 20. Likewise, for every unit of product B, we gain a contribution of 24 Rand. So column B's value is positive 24. We have now set up our initial matrix. In this initial matrix, we are not producing anything. So our slack variables represent our full capacity for each resource. Also, our contribution is 0. We now want to start producing and making some money. But which product should we produce and how much? To answer these questions, we need to pay attention to the contribution line. Here we see that the contribution offered in both columns, A and B, is positive. This is very important. As long as there are positive numbers in this contribution line, it means that we can make more money. So we will know that we have reached the optimal solution when both columns have either zeros or negative numbers. So now I know that producing both A and B will make me more money, which should be obvious because I'm currently getting a contribution of 0. So which product should I make first? This is easy. I make the one that gives me the highest contribution. This is product B with a contribution of 24. Once I have selected product B to make, I need to identify which constraint limits its production. To do this, I am going to assume that I only make product B. I will therefore allocate all available resources to product B and see how much I can make. Starting with materials, I see that I have 3,440 units available. Product B uses 4 units of materials, and therefore I can make a maximum of 860 units of B. I now do the same for the labor constraint. I have 5,760 hours. Each unit of B takes 16 hours. Therefore, I can make 360 units of B. For the machine hours, I have 5,520 available hours, and each unit of B takes 10 hours. Therefore, I can make 552 units of B. The constraint affecting the sales of A does not affect product B. Therefore, it is not applicable in this case. Based on these calculations, I now see that the main constraint for product B is labor hours. It limits my production of B to 360 units. Now that we have identified the labor constraint as constraining product B, I need to rearrange the terms to get B as the subject of the equation, rather than the slack variable S2. Once we have done this and simplified the fractions, we get B is equal to 360 minus 3/4 A minus 1/16 S2. Now we can substitute B in for all other equations. Let us begin with the materials constraint. We begin with S1 is equal to 3,440 minus 8A minus 4B. We then replace B with 360 minus 3/4 A minus 1/16 S2. We multiply this out and simplify, and we get S1 is equal to 2,000 minus 5A plus 1/4 S2. We now do the same with the machine hours constraint. Pause the video and give it a try on your own and see what you get. Great, so following the same logic as with materials, we should arrive at S3 is equal to 1,920 minus half of A plus 5/8 of S2. Our next constraint is the sales of product A. As B is not present in the formula, the equation remains unchanged. Finally, we need to substitute B into our objective function. We do this in the exact same manner that we did all the input constraints, and we arrive at C is equal to 8,640 plus 2A minus 3/2 S2. So now we have our revised constraints based on producing 360 units of product B. We can use these to develop our second matrix. Notice here, however, that A and S2, our labor hour slack variable, are on the right-hand side of the equation and will now form the columns. Otherwise, I construct the second matrix in the same way as the first matrix. So for the materials constraint, I have the unused capacity of S1 being 2,000 materials. Under A, I have -5, and under S2, I have plus 1/4. My second line no longer relates to labor hours, but has now been replaced by the production of B. So I am producing 360 units of B. Column A is -3/4, and column S2 is -1/16. I then do the same for S3. Under the quantity column, I have S3 is equal to 1,920. When producing 360 units of B, I am left with 1,920 unused machine hours. Column A is -1/2, and column S2 is +5/8. Next, we do S4. Under quantity, we have S4 is equal to 450. Under A, we have -1, and under S2, we have 0. Finally, we have our contribution row. When we produce 360 units of B, we will make a contribution of 8,640 Rand. We have +2 under column A and -3/2 under column S2. We now have our second matrix. The quantity column shows how many of the products we are making, in this case 360 units of B, the contribution we make, in this case 8,640 Rand, and how much unused resources we have. Now let us draw our attention to the contribution row. Notice that column A has positive 2, while column S2 has a negative 3/2. The fact that we have a positive 2 means that we have not yet maximized our contribution. We can maximize it more by producing more of product A. We can reduce production of B by 3/4 of a unit to increase production of A by 1 unit, and this will enable us to gain an extra 2 Rand in contribution. The next step then is to find out which constraint will limit our production of product A. As we did with product B initially, we take the capacity of each resource and divide it by the usage under column A. For materials, we take the 2000 units and divide it by 5 under column A to get 400 units of product A. The labor constraint is not applicable in this case, as we already know it is fully utilized. For each unit of A I produce, I need to give up 3/4 of a unit of B. Therefore, we ignore this constraint. For machine hours, we have spare capacity of 1920 hours. We divide it by a half in column A to get 3840 units of A. Finally, for sales of A, we take the capacity of 450 units and divide it by 1 to get 450 units of A. Here we see now that the lowest units of A we can produce is 400 units. Therefore, materials are our constraint. Now that we have identified the materials constraint as constraining product A, we need to rearrange the terms to get A as the subject of the equation rather than the slack variable S1. Once we have done this and simplified the fractions, we get A is equal to 400 minus 1/5 S1 minus 1/20 S2. As we did with product B earlier, we now have to substitute A into all our other constraints. Let us begin with the production of B. We substitute in the new value of A, and once we multiply everything out and we simplify, we get B is equal to 60 plus 3/20 of S1 minus 1/10 of S2. Now it is time for the machine hours constraint. Pause the video, give it a try, and see what you get. Great, so I get S3 is equal to 1720 plus 1/10 S1 plus 3/5 S2. We do the same for our sales of A constraint, and we get S4 is equal to 50 plus 1/5 S1 minus 1/20 S2. Finally, we substitute A into our contribution function, and we get C is equal to 9440 minus 2/5 S1 minus 7/5 S2. We can now use our revised constraints to update our matrix. Notice this time that only S1 and S2 are on the right-hand side of the equal sign. Therefore, the columns are now headed S1 and S2. We can then update our matrix in the same way we did our initial and second matrices. Now if we look at the contribution row, we see that both S1 and S2 columns have negative numbers. This means that any changes to our current production mix will reduce the contribution. As we are trying to maximize our contribution, the negative signs in both columns indicate that we have reached our final matrix. If we now turn our attention to the quantity column, we see that our optimal production mix is 400 units of A and 60 units of B. This matches what we achieved under the graphical approach for this example. We can also see that at this production level, we will be generating a contribution of 9,440 Rand. We will have excess capacity of 1,720 machine hours and unmet demand of 50 units of product A. You will notice that neither S1 or S2, which are the materials and labor hour slack variables, are present. This is because both of them have been fully utilized. The next important issue we can use the final matrix for is calculating the shadow price. We can calculate the shadow price of 1 unit of material. Remember that S1 is the slack variable for materials. If we decrease materials by 1 unit, we need to give up 1/5 of a unit of A, and we can then produce an extra 3/20th of a unit of B. Alternatively, if we increase materials by 1 unit, we can gain 1/5 of a unit of A, and we lose 3/20ths of a unit of B. Notice that we have swapped the signs. Let us assume that we will gain a unit of materials. We will increase production of product A by 1/5 of a unit at a contribution of 20 Rand per unit. However, we will need to decrease production of product B by 3/20ths of a unit at a contribution of 24 Rand per unit. This will give us a shadow price of 40 cents per unit of material. Therefore, the company will be willing to pay up to 40 cents more than the current purchase price per additional unit of materials. The same logic can then be applied to calculate the shadow price of labor. That brings us to the end of our series on linear programming. We hope you enjoyed it. Be sure to watch our other videos, and we will see you next time.